So, we were talking of magnetic field due to currents, and to calculate that we have our favorite Bhatt-Savart equation, and that is for a current element dB is mu naught by 4 pi and I dl and then cross r divided by r cube, and this is for a linear current, and using this we calculated the magnetic field due to a straight wire current and circular loop with a straight wire current, long straight wire current. We got the equation that if this distance is r, this perpendicular distance is r, then the magnetic field here is mu naught I over 2 pi r in phi cap direction. If this is z axis, then the phi direction is around this, and magnetic field lines are of that nature that we discussed. If you have two parallel wires carrying current, then they attract, the parallel currents attract and anti-parallel currents repel. That is also important in the sense that prior to 2019 this was used to define the SI unit of current. So, the derivation is if you have a current I1 here, if you have a current I2 here, and it is a long straight wire, and what do we mean by long straight wire? You cannot have current in an isolated wire, it has to be a circuit. But then the circuit may be completed through a very large kind of circuit, and from this side also. And if you are interested in finding the field here, field here and the force, then possibly those far away part of the circuit are not contributing much, and then you can use only this part. And if I take any length here of some dl, the magnetic field at this location, because of this entire wire, entire circuit, entire long wire, that magnetic field B here will be given by this equation, which is mu naught times I1 and by 2 pi and then r. Long straight wire, and then current, this magnetic field at a distance r, perpendicular distance r, that is given by this in phi cap direction. So, if you consider this current element I2 dl, this much of current element, and ask what is the force because of this magnetic field on this piece of wire, then that force will be I2 and this dl vector and cross B, and this dl is in the z direction. This is our phi direction, so this is our z direction, so this is z direction, dl is in z direction, so it is dl k cap and cross B is this mu naught I1 by 2 pi r and phi cap, and that is mu naught I1 I2, this I2, this mu naught, this I1, and then divided by 2 pi r, and then dl k cap cross phi cap. So, you have S, you have phi, you have Z. So, k cap is this one, k cap, and then phi cap is here. So, that means k cap cross phi cap minus of S cap. All right. If you go cyclic, S cap cross phi cap, you will get k cap, phi cap cross k cap, you will get S cap, and S cap and this k cap cross s cap, you will get phi cap, and it is reverse, you get a minus sign. So, this for k cap cross phi cap, k cap cross phi cap will be minus s cap. So, the force here is towards this first current, that is why we say that parallel currents attract. These two wires will attract each other. Every element on this wire will experience a force towards this other wire, and similarly every element of this wire will experience a force towards the other wire. So, the parallel currents attract, and the force per unit length of any wire. So, this is F, this is dF, this is dF, and then divided by this dl. So, force per unit length is mu naught I1 I2 divided by 2 pi r. This was used to define an ampere. If you adjust your current in such a way that the two currents in the two wires are equal in magnitude and they are parallel in the same direction, and force per unit length of a wire because of the other wire is 2 into 10 power minus 7 Newton, and you keep the wires at a separation of 1 meter. In that case, the current, whatever is the current magnitude of current which is common, equal currents, that was defined to be 1 ampere, but in 2019 the definitions have changed and this definition is now a history. Then we also used this Biot-Savart law for magnetic field due to circular current. So, we had a circular current, this is the circuit and there is a current I, and then we wanted, the radius of this is A, and we wanted magnetic field at a certain point at a distance r from the center along that axis, and then we derived, using this we derived the magnetic field here at this point. The magnetic field is what? Mu naught I A square by 2, this will be A square plus R square and 3 by 2. This was the expression we derived. If you put r equal to 0, so that you are at the center, so, and this is of course in k cap direction, the current is in phi cap direction, the magnetic field is in k cap direction at the axis. And if you put r equal to 0, you are at the center here, then r will be 0 and this will be mu naught I, and this is a square here, this will be a cube here, so 2a. So, at the center it is mu naught I by 2a, and this is a check. In fact, if you remember this at the center expression, this is simpler to remember, mu naught I by 2a, this is a check. By putting r equal to 0, it should reduce to this one. Now, what happens if r is much greater than a? As compared to this a size of this current loop, suppose you are at a large distance and you are asking the magnetic field there and how it varies with this r, then it will be, your a is very small and it is r square plus a square. So, this a square can be neglected here, but this a square cannot be neglected because it is standing alone. This a square is in front of r square plus a square. So, if r is very large as compared to a, then you can neglect this and then see what happens. In that case, b is equal to mu naught I a square and then divided by 2, and this a we are neglecting. So, this will become r cube. So, this will become r cube. Okay, and this will be in k cap direction, of course. And if you multiply it by pi here and pi here, then this is pi a square is the area of this current loop, this area, and this is current I. So, you remember I times area and then k cap. This is the magnetic dipole moment of this current loop, right. The current loop is, the dipole moment is m, and that is given by I times area vector, area vector. This is the magnetic moment. Why do we call it magnetic moment? The magnetic field, if you have a magnetic field and then you have a current loop and uniform magnetic field, then the torque by a uniform magnetic field on a current loop that is equal to torque is m cross b. This is dipole, magnetic dipole moment, and this is magnetic field, and magnetic dipole moment is defined as I times area. So, if this is the current loop, we take this area I times that area in the direction perpendicular to the plane of the loop, that is this m cross b is the torque, and this resembles the torque on an electric dipole due to a uniform electric field, and that is written as torque is P cross E, where P is the electric dipole moment. And this derivation is very simple. Electric dipole moment, you can take it as 2 point charges minus q and plus q separated by some distance, and then if you have electric field in this direction, electric field, then there is a force out here, this force is q times E, and then you have a force here which is again q times E. And if you take torque of these two forces about any point here or here or here or here, any point, that finally turns out to be this P cross E, where P is, if this distance is d between the two charges, then P is q times d, and from negative charge to positive charge, that is the direction. Now, this expression is identical to this expression, and we define this moment dipole, magnetic dipole moment m, provided you take current times area vector as the definition. We do not have minus q plus q type of thing here, this is a loop, current loop, but then yes, you can still define a magnetic dipole moment, and it is this. And for an electric dipole also, if you remember, if you take electric dipole minus q plus q and then calculate, this distance is d, and then calculate the magnetic field at a far away point on the perpendicular bisector at a distance r. Easy, this, from this q you will write the electric field, it will be like this, and from minus q, this minus q, it will be like this, and then the resultant will be this will be the resultant electric field, and simple to calculate. And if you calculate, you find that E, which is 1 by 4 pi epsilon naught here, and then the dipole moment, electric dipole moment, and divided by r cube. And if you take the point here on this axis known as end on position. So, this distance is r, this distance is r, and at this point you ask what is the electric field. So, here also it is simple. From this plus q you write the electric field. This will be 1 by 4 pi epsilon naught and q divided by r minus d by 2 whole square, and similarly from here, and then you do this calculations and take the approximation. This r is much larger than this separation d, and then you get E is equal to 1 by 4 pi epsilon naught and 2p by r cube. Now, if you compare this expression, magnetic field due to a current loop on its axis is mu naught by 4 pi 2m by r cube, and here it is 1 by 4 pi epsilon naught 2p by r cube. So, it varies as 1 by r cube, this also varies as 1 by r cube. Here you have 2 times electric dipole moment, here you have 2 times magnetic dipole moment, and this quantity mu naught by 4 pi and this 1 by 4 pi epsilon naught, often if you are writing expressions from electrostatics and there is a corresponding situation in magnetostatics, then this 1 by 4 pi epsilon can be replaced by mu naught by 4 pi, and you make a smooth transition from formula wise electrostatics formulae to the magnetostatic formulae. So, this situation is very similar to this situation. This we are calling an electric dipole and dipole moment P. Similarly, here we are calling it a magnetic dipole and magnetic dipole moment M. But then the point is on this dipole axis. This is the dipole moment direction. The p direction is this. This is the p direction. Dipole moment is in this direction, negative charge to positive charge, and the direction, in the direction of magnetic moment, I have taken this point at a large distance r. Here we have taken this point which is at a large distance of r, but then it is not along the dipole moment direction, it is perpendicular to that. And this formula differ by this 2, and here this is matching with this one. So, we will say that our magnetic dipole moment, if I compare with electrostatic situation, should be, this point should be on the axis, and that is here. Our dipole moment is I times area vector, and this area vector is in this direction. This is area vector is in this direction, and magnetic moment is also in this direction. So, all this prompts us, all this suggests us that even if it is not the case, we know that this will not be the case, but let us consider this current loop as a combination of 2 point magnetic charges, one negative magnetic charge and one positive this magnetic charge placed at a separation of this small d. So, we are trying to replace this current loop by a fictitious virtual imaginary system. Then all the laws we will formulate will also be imaginary, keep this in mind, but our mathematics will become quite simple if we do that. And what is that? Let us think that this current loop is equivalent to a combination of 2 magnetic charges like this, minus qm, m for magnetic, and plus qm. two magnetic charges, so that there is a dipole moment in this direction at a separation d. This is the separation d, and we define dipole moment as qm times d in this direction, negative magnetic charge to positive magnetic charge. Okay. Then we will have to write some more equations, imaginary equations, not real. These are not real things, we are only making. So, B due to qm at certain point, there is a general rule we are writing. You have a plus qm here, and then at this point you are asking what is E, and let us say from this plus qm to this point, this vector is r. Then we will say that electric field here will be mu, the magnetic field. So, the magnetic field will be mu naught times 4 pi. In place of 1 by 4 pi epsilon naught, we will write mu naught by 4 pi. So, 1 by 4 pi epsilon q by r square. So, qm divided by r square is the magnitude, and the direction is radially away from this plus qm. So, you can write r cube here and r vector here. So, due to the charge qm, the magnetic field at this position with position vector r taking the origin here is given by this. We are just taking it from electrostatics. In electrostatics, we know that if you have a charge q and then you have a point here and this is r and you want electric field here, that will be 1 by 4 pi epsilon naught and then this q divided by r square. So, we are just writing this in our framework, and it is this. And similarly, for the negative charge, it will be towards that negative magnetic charge, and then you can write magnetic field due to this, magnetic field due to this, and do all the calculation and get the same result. So, this is how we sometimes model and say that this is the magnetic moment direction, and this situation is, that means the current loop we are replacing by, this current loop we are replacing by two charges minus qm and plus qm at a distance r, and I times pi a square should be equal to qm times d, right, because this is, we know that this is the magnetic moment, and if we do this mathematical modeling, then we will say that the magnetic moment is qm times d. So, we have to choose our qm and choose our d in such a way that this equation is satisfied, then we will get the right kind of equations. So, if I take this current loop equivalent to this, then this situation is same as this situation. Along the axis dipole moment direction, you have a point here also, along the magnetic moment direction you have a point there. So, from the electric field electrostatics, we simply write from here this equation without going through the Bhatt-Savart law. Now, the immediate example I can give where it shows its strength, and that is when you have a current loop I, this radius is a, and we want magnetic field at a large distance from this current loop, but not along the axis, but in the plane of the current loop. In the plane of the current loop here, this is r, large as compared to a. So, I have a circular current loop, and then I am asking the magnetic field not on the axis, but in the plane at a large distance. Now, if you use Bhatt-Savart law, to calculate the field, the integrations will be fantastic integrations and only computers will be able to solve it. But here if I use this modeling, we say that this current loop is nothing but it is a combination of minus qm and plus qm. This is plus qm and this is minus qm, perpendicular to the plane of the loop, and we need the magnetic field here at a distance r. Now this situation in electrostatics is same as this situation, this figure. You have minus q plus q, magnetic moment is in this direction and you want electric field at the perpendicular bisector, and here also in this also minus qm plus qm and perpendicular bisector large distance are what is the magnetic field. So here we know the equation, this is the equation, this is the equation, E is 1 by 4 pi epsilon naught P by R cube. So 1 by 4 pi epsilon naught, for this we will write mu naught by 4 pi, and then P we just write m and we get the equation. So this B here will be mu naught by 4 pi and then m, and here it will be R cube, that will be the magnitude, and of course we know the direction in that plane going into. If the current is this way, the magnetic field lines will go and then dip there in this plane. Okay, from here they will go like this, so the direction is this. So that is all about magnetic field due to linear currents, and in the next lecture we will start talking of surface currents and magnetic fields because of the surface currents.